So the second force that we want to go ahead and explicitly calculate out the work done by that force is when we have work done by a spring. So here I have a mass that's attached to the end of a spring, and you'll notice that this dotted line with the x0 designation, that's showing me where the equilibrium point is for the spring. So that's, if you let the mass go, that's where that mass is going to end up. It's where the spring wants the mass to be. Well, what I'm going to do is I'm going to apply some force that pulls the mass away from equilibrium. And as I do that, so I pull it through some distance, there's a spring force that's acting to try and pull the mass back towards equilibrium. Well, as I pull farther, so it requires a larger applied force because there's a larger spring force. So the more I pull the mass away from equilibrium, the larger the spring force is. But notice still the spring force points back towards equilibrium. So one of the things that we need to make sure we understand is that the spring force always pulls the mass back towards equilibrium. It's what's known as a restoring force. Even if instead of pulling the mass to the right, we were pushing the mass to the left, we would still have a spring force that is trying to push the mass back towards equilibrium. Well, what that means then is before I worry about any calculation, I know what sign I should get for the work done by the spring based on how the mass is moving. If the spring force always points back towards equilibrium, if my mass is moving back towards equilibrium, the spring does positive work in that case. On the other hand, when the mass moves away from equilibrium, because that spring force is again always pulling back towards equilibrium, that means the spring does negative work on the mass as it moves away from equilibrium. So if we want to think about the calculation, well, again, the first thing we have to recognize is that the spring force is not constant. Right? The farther I pull the mass away from equilibrium, the larger the spring force gets. Which means I can't simply use the expression that we've been using to calculate the work done by a constant force. This will not just be the magnitude of the force times the magnitude of the displacement times the cosine of some angle between them. I can't use that expression here because the spring force isn't constant, and that expression only works for constant forces. Instead, I've got a couple different ways that I can calculate out the work done by a spring. The thing that's the same about both these, there's a 1/2 sitting out front, there's a k, which is the spring constant, sitting in both of these expressions, and then I've got a couple of distances squared. The differences, of course, is in this first version, I've got the minus sign out front, and then I've got x final squared minus x initial squared sitting inside my parentheses. In the second one, I've taken that minus sign and distributed it inside the parentheses. So there's no minus sign out front, but now what I've got is x initial squared minus x final squared. Algebraically, these two equations are exactly the same. I don't care which one you use, it doesn't matter. They should give you the same answer. Mostly this is just sort of you decide which one of these you're more comfortable with. If you don't like the minus sign sitting out in front, then use this equation. If you know that x initial out in front before x final is always going to freak you out, then use this equation. It doesn't matter, pick one, let that be the way that you calculate the work done by a spring, and just get comfortable with it. We said we know what sign we have to get based on how our mass is moving. So let's make sure that this equation is consistent with that answer. And so I'll just go ahead and pick the one where the minus sign has been distributed, and so I've got 1/2 k times x initial squared minus x final squared. Well, if my mass moves away from equilibrium, so this is the case that's pictured here. So my mass was here, there's its initial displacement from equilibrium. I've pulled it out this farther distance, so notice now there's a larger displacement from equilibrium. So my x final is greater than x initial, which means that when I take those two things, square them, and subtract x initial squared minus x final squared, because this was the bigger thing, when you square and subtract, you're going to get something that's negative, which means I've got a negative inside this parentheses. Multiply that negative term times a positive k times a positive number, and sure enough, you get negative work as the mass moves away from equilibrium, which is what I knew I needed to get. On the other hand, if the mass moves towards equilibrium, so that's sort of this picture in reverse, where now my mass is moving back in this direction. Well, in that case, the initial displacement is greater than the final displacement, which means I've got something bigger squared minus something smaller squared, so this is now positive. So the term in my parentheses is positive, multiplied by positive k, multiplied by a positive number. Sure enough, the work done by a spring is positive as my mass moves back towards equilibrium. Whichever of these expressions you choose to use for the work done by a spring, they're clearly going to give us the right answer for what the sign should be for the work based on whether the mass is moving away from or towards equilibrium.